Okay, so let's talk a little bit about electromotive force, or sometimes it's just called EMF. So the movement of electrons is analogous to pumping water from one point to another. So let's okay, you're trying to pump water from one point to another. Um, Generally speaking, water moves from a point of high pressure to a point of low pressure. So a pressure difference is required. The work in moving the water through the pipe depends on the volume of water and the pressure difference. You know, if you're trying to go from the top of a waterfall to the bottom, that's going to be pretty easy. And if it's just a few drops of water, it's going to be pretty easy. If you're trying to pump the water back up to the top, that's going to be a lot harder. So it's the same thing with the movement of electrons. So an electrical charge wants to move from a point of high electrical potential or high electrical pressure to one of low electrical potential. And in the same way as the water, the work expended will depend on the amount of the charge and the potential difference, how easy it is for the electron to move. Okay, so the potential difference is the difference in electric potential between 2 points. We can measure this quantity in volts. A volt is the SI unit of energy of this kind, and it's equal to 1 joule per coulomb of charge. F is called the Faraday's constant, and it is a constant. It's the magnitude of the charge on 1 mole of electrons, which equals 96,500 coulombs. So, to move 1 mole of electrons through a circuit, the work done by a voltaic cell is the product of F, the Faraday's constant, times the potential difference, which gives you then work, which is in joules, is going to be the Faraday constant in coulombs times the volts. And notice that coulombs will cancel, and so your work is in joules. Work is negative because it's done by the system. So when you normally operate a voltaic cell, the voltage across the electrode is less than the maximum. And so because the electrons are actually flowing, it reduces the electrical pressure, so you can never get to the maximum. So actually the cell voltage has its maximum when no current flows. It's sort of like you can't measure the pressure of a water pipe as well if the water's flowing. All right, so the maximum potential difference, or the maximum voltage between electrodes of a voltaic cell, is called the electromotive force, or the EMF of the cell, or sometimes it's called E cell, the electromotive force of a cell. You can measure it with a voltmeter. So we can write an expression for the maximum work attained by a voltaic cell. So that's what our goal is to get as much work out of our voltaic cell as possible. So if we talk about N being the number of moles of electrons, then work, the maximum amount of work, equals negative N, being the number of moles, times Faraday, which is the constant for 1 mole, times the E cell, which is the voltage. And it's work done by the system, so that's why it's negative. So let's look at an example. The EMF of an electrochemical cell below is 0.650, so we don't need to figure that out. It's told to us. What is the maximum electrical work of this cell if 0.5 grams of hydrogen is consumed? Well, we know that the maximum work equals minus N F E cell. So we know F because that's a constant. We know E cell because that's given to us, 0.650, but we don't know what N is. N is the number of moles of electrons that are moved. So let's figure that out first. So we have to look at the half reactions. Mercury is reduced with 2 electrons to give us mercury liquid, and hydrogen is oxidized to give us 2 electrons. So the number of electrons, N, equals 2 in this case. So we can plug that into our equation. The maximum amount of work is negative 2 times F, which is 9.65 times 10 to the 4th coulombs. times the voltage, 0.650, and since that's in volts, so coulombs times volts is joules. And so the maximum amount of work is 1.25 times 10 to the 5 joules. And the negative just indicates that the work is being done by the system, so out of the system. So that's how much for 1 mole of hydrogen, because this balanced chemical equation has 1 mole of hydrogen. So to have 0.5 grams of hydrogen, we have to just calculate. So 0.5 grams, there's 2 grams per mole. And we see that the maximum amount of work is negative 1.25 times 10 to the 5th joules per 1 mole of hydrogen from the balanced chemical equation. And so for a half a gram of hydrogen, we'll be given off 3.09 times 10 to the 4th joules for a half a gram of hydrogen to react according to this reaction. So the cell EMF is a measure of this reaction. We know that the anode is the oxidation and the reaction at the cathode is the reduction. We can look these values up. And so the overall cell is actually a combination of the two potentials. So the E cell is the oxidation potential plus the reduction potential. The reduction potential is a measure of the tendency to gain electrons. How likely is something going to gain electrons in the reduction half reaction? Now, the oxidation half reaction is the reverse of this, because the oxidation potential is how willing is it to give up electrons. So they're opposite. They're the same exact number, but they're opposite of each other. So the oxidation potential is then the negative of the reduction potential for the reverse reaction. So actually all potential charts give the reduction potential, and you have to figure out for your example, which is your oxidation potential, which one is being oxidized, and switch it. So we can look at tabulated reduction potentials. So let's look at this zinc copper that we looked at earlier. Okay, so because the zinc to zinc 2 plus is on the left, that's the oxidation, and the cathode, the reduction, is the copper. So the two half reaction, zinc is being oxidized because it's on the left hand side, and copper is being reduced, it's on the right hand side. So the zinc is being oxidized. So we can write that the electrode potential for zinc, we know we can look up the reduction for zinc, so we know that the oxidation potential for zinc is just the negative of the reduction potential for zinc. So here we're showing you the oxidation for zinc, the reduction for zinc is, we can look that up, E zinc. The oxidation then is the opposite sign, and that's what we're looking for in this problem. So the copper half reaction is a reduction, so we can just read that off the chart. So the ECU is just the reduction potential for copper. So we can look these numbers up. So it turns out that E cell is going to be E of copper, because that's the reduction, plus the opposite sign of the E of zinc. And so really the E cell is E copper minus E zinc. So it's an easier way of looking at it. You don't have to, you just figure out which one is the oxidation, and that's minus then. So in general, to find the E cell, you always subtract the anode potential from the cathode potential. So E cell is just E cathode minus E anode. It's an intensive property, so that means it's independent of the amount of species of the reactant. So it doesn't matter if you double it, double the half reaction, the E cell or the E for the reduction potential is going to be the same no matter if you double it or if it's single, it's going to be the same. Now the work is going to be different because of different electrons, but the actual E cell value or the E reduction value is going to be the same regardless of how many electrons or if you double it or whatever. Okay, so just like a lot of things in chemistry, you could have lots and lots of situations. And so whenever we're doing these kind of calculations, we're always going to be using standard. We look up standard electrode potentials, which means that if there's a concentration of some sort, they're 1 molar. If they're at a certain pressure, they're 1 atmosphere. A certain temperature is 25 degrees Celsius. So that's what we'll be looking up. And you'll notice that it's E cell with the little circle, which indicates standard condition. Now, when it's really hard, you can't just measure a potential because you always have to measure it with respect to something else. So individual electrode potentials require that we have a reference electrode. And so that turns out to be, they're going to assign one of the electrodes a potential of 0. And then you can measure everything else in comparison to it. So it turns out that the reference chosen to be 0, have a 0 potential, is the standard hydrogen electrode. So then the standard electrode potentials are measured in relation to this hydrogen reference. So you could have picked any one, but they just happened to pick the hydrogen. So this is just what you see in your book. Appendix I has a more extensive table, but this is table 19.1 in your book, and you could look here or in your book or in the appendix. So let's say we are measuring the EMF for the cell composed of zinc connected to hydrogen. If you were to measure it, you would get a value of 0.76. So that would be, we're comparing it, the zinc electrode, to hydrogen. Since zinc in this case is the anode, it's listed as the reduction potential then is listed as 0.76, negative 0.76. So they're all relative to each other, and so they're all listed as reduction potentials in the book. So these standard electrode potentials are useful in determining the strength of oxidizing and reducing agents under standard conditions. So if something is reduced, we know that it is an oxidizing agent, right? So if something's reduced, it's the oxidizing. So the thing that is the strongest oxidizing agent, which means that it is the thing most likely to be reduced, that will be the species that has the largest, most positive E value. So if you're looking at the chart we just looked at, that would be F2 gas. Now, if something is being oxidized, then it is the reducing agent, the thing that is being oxidized. And the strongest reducing agent, the thing being oxidized, will be the species that has the smallest, or which would be a negative, the most negative E value. So the thing that is most likely oxidized will be, on this list, will be lithium. So the one that has the more negative number will most likely be oxidized. So if we look at this reaction, so we have cadmium plus 2 electrons giving us cadmium solid. It has an E0 value of negative 0.4. And then we have silver, reduced of silver, and he has an E0 value of 0.8. So obviously the reaction is not going to be 2 reductions. One of these is going to be oxidized and one of these is going to be reduced. So how can we figure out which one's which? Well, so we're going to have to reverse one of these to figure out what's being oxidized, which one is more likely to be oxidized, and which one's going to be reduced. So it turns out that the more negative number, remember, is the one that is more likely to be oxidized. That turns out to be cadmium, and so that's the one that's going to get reversed. So cadmium has a more negative electrode potential. It means it's more likely to be oxidized than silver is, and so silver is more likely to be reduced than cadmium. So let's rewrite this. So if we reverse the half reaction of the cadmium and make it oxidation, we also have to change the sign. So now it becomes positive 0.4. Silver we leave as it is. It turns out that to write this reaction, the complete reaction, we're going to have to double the silver reaction so that when they're added together, the electrons can cancel. However, as we said earlier, this doesn't affect the half cell potential, and so the E naught numbers don't change at all. So if we double the silver, and then we add them together, the electrons cancel, and we have the balanced chemical equation. The E cell for this reaction is 1.2. So if we were to put cadmium in cadmium ions, silver in silver ions, and hook up a voltage, electrons would flow from the cadmium to the silver, and you would have a voltage of 1.2. So if we wrote the cell notation, since cadmium is being oxidized, it goes on the left. Silver is being reduced, it goes on the right. And then note that the E cell, we could have, if we knew which was the cathode and which was the anode, we would just look up the numbers. E cell equals E cathode minus E anode. So the E cathode is 0.8, and the E anode is negative 0.4, so 0.8 minus a negative 0.4 gives us 1.2. So let's look at an example. Calculate the standard EMF for the following voltaic cell using standard electrode potentials. And then what is the overall reaction? So because of the way that this is written, the aluminum is on the left, meaning that's the anode. The iron is on the right, meaning that's the cathode. So iron's being reduced and aluminum is being oxidized. When we look up the half reactions, of course, we're always looking up the reduction potential. So aluminum being reduced to aluminum metal has a E naught of negative 1.66 volts. Iron reduces to iron solid with 2 electrons, and that gives us a negative 0.41. And as we said, the thing that is the most negative is most likely to be oxidized. So this is a voltaic cell because aluminum is more likely to be oxidized, and it is the anode. So to write the actual reaction, we need to reverse the aluminum to figure out the EMF. We could either figure out E naught is cathode minus anode, and since our cathode is negative 0.41 and our anode is negative 1.66, we could take negative 0.41 minus a negative 1.66. Which is 1.25. But let's do it by reversing. Let's see what happens on the next slide. So if we reverse the first half reaction and its half cell potential, so aluminum being oxidized has an E naught of 1.66. We keep the second the same. It has a potential of negative 0.41. So if we add these together, but in order to get the overall reaction, we have to balance the electrons. So we see that one aluminum loses 3 electrons, one iron gains 2 electrons. We have to even them out, so the least common multiple is 6. So we have to multiply the aluminum reaction by 2, and we have to multiply the iron reaction by 3. However, it doesn't matter what you multiply it by, the E values, the potential values are not changed at all, so they stay the same. And so we have the same number of electrons. When we add the equations together, we get 2Al plus 3Fe2 plus gives us 2Al3 plus 3Fe. And as we said earlier, the potential value is 1.25 volts. So if you measured this, you would get 1.25 volts. Again, you could do it either by switching the reduction potential to the correct one to the oxidation potential and change the sign and add them together. Or you could use the equation E cell equals E cathode minus E anode and just pull the values from the book. So again, that the voltaic cell is one that by definition is spontaneous as written. So for this to be true, the stronger oxidizing agent, the one with the more positive potential, should be a reactant. And that means that the E cell should be positive. Remember back in chapter 18, we talked about delta G, and delta G is actually the maximum useful work of a reaction. Delta G equals W max. So we can put these two equations together that W max we saw in this chapter is equal to negative NFE cell. So delta G equals negative NFE cell. So for a voltaic cell, the electrical work, where N is the number of moles of electrons transferred. And so that's when this becomes important. The delta E doesn't change, but the N comes into this equation. So delta G just equals negative NFE. Note that if E is positive, that means delta G is negative. So E, if you have a positive cell potential, that is a spontaneous reaction that gives a delta G which is negative, and so it is spontaneous. All right, so let's determine if the following reaction occurs spontaneously in the direction indicated under standard conditions. So we have copper being reduced to copper metal, copper ion being reduced to copper metal, and iodine ion being oxidized to iodine solid. First, you have to identify which two species are the ones that are being reduced, And it turns out that copper ion, copper 2 plus, is being reduced to copper. And in the reverse reaction, the I2 would be being reduced to I negative. So which one is the stronger oxidizing agent, or the thing that is more likely to be reduced? So it's the one that is more positive, or in other words, the one further down the chart. So we look up I2 being reduced, and we look up copper ion Cu2 plus being reduced. Cu2 plus is a 0.34. And be careful, because there's Cu2 plus being reduced to Cu plus, and then there's a little bit further down Cu2 plus being reduced to copper solid. So be careful that you pick the right one. And then I2 being reduced is 0.54. So which one's more likely to be reduced is going to be the iodine. Since the stronger oxidizing agent, or the one that is more likely to be reduced, is a product in this case, this is not a spontaneous reaction. So this would actually be spontaneous in the reverse direction. So if you had iodine and copper, they would react to give you copper ion and iodine ion. Another way that you can do it is just to find the E cell for the reaction, figure out which is being oxidized. So we know that according to the reaction that we have earlier, the copper is being reduced, so that's 0.34. We know that the anode is the oxidation, and the value is 0.54. E cell is, so actually E for the oxidation would be negative 0.454. So the E cell is the cathode minus the E for the anode. So 0.34 minus 0.54 gives you a negative 0.2 volts. If E cell is negative, the reaction is not spontaneous. So that's just another way to do that same problem.